Hello, for this lab, we'll be looking at the motion of a falling object. For the table of contents, first we'll be looking at the different physics concepts involved, followed by a demo on Tracker, some of the key results, a model demo, followed by some of the graphs, and we'll overlay them with and without the drag force, after which we look at some results and possible key improvements. In terms of the physics concepts involved, the main one is Newton's second law of motion, which we will be using to update both the position of the moving ball, the falling ball, as well as its velocity. In this case, unlike our previous lab report, the force is actually not zero, so we will have to take these into account when modeling the change in position and change in velocity, as well as look at the drag force when we add that into our model. The two forces primarily acting are the weight force downwards and the force of drag upwards, which is proportional to the square of the velocity, which the ball is moving at downwards. Now moving into a demo of Tracker. As you can see, in this case, we've dropped a ball from rest onto the ground. These are some of the key results on Tracker. We've also used a calibration stick, and we have made an axis the center of the ball at its initial position. Some of the key points for the Tracker demo is the fact that I've calibrated the center of the ball with the axis at the 0, 0 point. Another important fact is that I've chosen the diameter of the ball for the calibration stick, and the diameter of the ball is 0.1 meters on average. Some of the key results include the fact that this velocity of the ball is actually increasing once it was dropped because there is a net force downwards. As you can see, the slope of this graph is increasing. When looking at the velocity is more or less constant and it is also decreasing at this point where it starts to flatten once it reaches its terminal velocity due to the drag forces involved. Another key point of consideration is the fact that we have set the initial position of the ball based on the observed position of the ball on Tracker. I've also made sure to make the mass 0.5 kgs, which on looking up online was the average mass of a small football. This does matter to the result because force equals m times g, in this case because the force is not net zero. On updating the velocity, we can use this net force which we calculate previously, and we can update the position based on the velocity which we calculate using the force. For the model with drag, I have found an appropriate drag coefficient as well by making sure that the final position reached by the ball in the experimental setup is equal to the final position reached by the ball on the model. The delta t was set to 0.033, which is the average frame rate on Tracker. On running the demo, we can see the following. We can see that the mass was set, so was the time step. We can also see the initial position and the velocity vector being dropped from rest. We can also see g and the coefficient. In this case, we are going to keep the coefficient at 0 to make sure we can model without drag, and the model works fine. As you can see, there's only a force acting downwards. What's also important to see is that the velocity is constant. It is constantly increasing. Next, if we set the drag coefficient to be what we had set initially, we can see that the model will have some drag force acting upwards. As a result, the velocity will be decreasing. Eventually with time, it will be decelerating. On looking at some of our key results from the model, we can see that the model without drag actually reaches a further distance on the y-axis than our experimental setup does, which can be seen with this discrepancy. On adjusting for drag force in the model, you can see that this dashed line matches up perfectly with our dotted line. This is on adding a frictional coefficient of 0.08. Also on adding a particular initial velocity, which would be throwing the ball with some speed, which would be in this case 1 meters per second, which we have assumed, we can see that there isn't too much change really. The position versus time graph is increasing in slope, and after this 0.45 second mark, you can see it somewhat becoming constant. Similarly for the graph with an initial speed. What we do see is that it's covering a larger position in a given amount of time, but they both reach terminal velocity at about the same period of time, and an initial speed doesn't really affect the final velocity or the terminal speed too. Finally, on looking at some of our key results, we know that the forces acting on the ball are basically two. There's the weight force downwards and the drag force upwards. When the ball is initially dropped from rest, we can see that the gravity is definitely higher than the drag force, which is why the ball accelerates initially. And after a while, what happens is the drag force becomes equal to the gravity, which is why it falls at a constant velocity, which is the terminal velocity. Some improvements that we could potentially make to the experimental setup includes using a darker ball so that we can track it more appropriately. We could take better measurements for length using the calibration stick, and we could also measure the weight of the ball better. We could reduce glare and thus improve trackers' ability to track the ball. We could also take multiple videos and make sure that the ball is dropped without any force in order to average the results, reducing the overall error of the experimental setup.